So in this video, we're going to talk about an alternate way we can apply the Castigliano's method that will make our calculations a little bit simpler. So for these two-part equations to solve for the displacement at a point and the slope at a point, we're taking the derivative of the strain energy with respect to the force that's applied at that point. Okay, so for both of these equations, the derivatives are with respect to a concentrated force and moment, which are not functions of x. So because of this, since we obtain the derivative with respect to the concentrated forces and moments that are not functions of f, therefore we can take the derivative before we integrate to solve for our strain energy. Okay, so for bending stress, if you recall, the strain energy due to bending is equal to this integral here. So to find a displacement, alright, we can say if we take the derivative of the strain energy with respect to pi, we can take the derivative of the mz squared term with respect to the concentrated force pi, because the mz term is going to be dependent on that concentrated force. If we use our chain rule, what we end up getting is we get 1/2 integral from 0 to L 1 over e to the iz. We're going to get 2 mz times the derivative of mz dpi dx, alright, which will simplify down to the 2's will cancel out, and we'll end up getting the integral from 0 to L 1 over e to the iz, mz times the derivative of mz over dpi, alright, dx. Alright, so in a similar fashion, we can do the same thing for the derivative with respect to the moment at any point. So again, we're going to use just the chain rule on this term here. So our theta I at any point is going to be equal to 1/2 integral from 0 to 1 over 1 to the e iz, and then we're going to get 2 times mz with the partial derivative of mz with respect to our moment applied at that point dx. Okay, so if we again, the 2's will cancel out, and we'll end up with our integral from 0 to L 1 over e to the iz mz dmz dmi dx. Okay, so there are some advantages of using these two simplified equations. The first thing is that once we take the differentiation with respect to either dmi, the moment, or the concentrated force at the point, we can set any of dummy loads and moments equal to 0. This will simplify our integration. And then the second reason we're going to do it helps is that if the moment of z is a function of more than one load, the integration is significantly simplified, because if you take the derivative of that moment with respect to the concentrated force or the concentrated moment, all the other terms in that moment equation will get reduced down to just the one that's dependent on either the concentrated force at the point or the concentrated moment at the point. And we're going to do a few examples to show how the simplified method reduces the amount of work that you need to do in these integrals.